Okay, there's a lot of background noise here because I'm in my car, but we are going to continue talking about energy and thermochemistry, which is a part of thermodynamics. Where we left off, we were talking about the conservation of energy. We were talking about how energy can be transferred from the energy of motion to the energy of position. Kinetic energy is the energy of motion. Potential energy is the energy of position. We talked about it with the bicycle rider, and then we talked about how atoms and molecules can transfer their energies of movement. Let's see if we can draw that. So this is my very limited drawing, but here we have a bunch of atoms moving around. They have a lot of kinetic energy, and this is the arrow for the reaction. These atoms bump into each other, and they transfer their kinetic energy to energy of bonding or energy of position. Now that energy is stored in these bonds in between them. This is not balanced, so this is just an analogy or a rough diagram. Moving on. In order to talk about energy, we need to have units that we can measure the energy with. So the main unit we're going to use will be called the joule. So if you see anything measured in joules or J's, J is the abbreviation, we're talking about energy. I'm going to define it for you. Remember, we said our kinetic energy or energy of motion was equal to 1/2 of the mass of an object times its velocity squared. So somebody, I forget who, let me see if I can look it up. Of course, this is a little embarrassing. So James Joule, a British scientist in the 1800s, defined the unit of energy, and that's why it's named after him, Joule. His name was James Joule, and he defined it as the energy that a 2 kilogram mass would have. So if you just had something that was 2 kilograms, and if it was moving along at a velocity of 1 meter per second, and that it would have the energy of 1 joule. He made this his base unit. So 1/2 times 2 kilograms, because that's our mass, times velocity squared, so 1 meter over a second squared. It's going to give us, the 2's cancel, 1 kilogram meter squared per second squared. That's a joule. Only we don't, so we could write every joule as kilogram meter squared second squared. It's a derived unit, but we don't. This is too much writing. We just say J, and J means all this. J for joule. Calorie is another unit of energy that you need to be familiar with. We abbreviate that CAL. And a calorie used to be defined as the energy needed to raise the temperature of 1 gram of water. That's my water. 1 degree Celsius. But now 1 calorie is defined as 4.184 joules exactly. So that's what it is. Both of these are pretty small amounts of energy. So sometimes we talk about kilojoules, sometimes we talk about kilocalories. Actually, the calories that we measure our food in are really kilocalories. Okay, so if we're going to study energy changes, we need to define the system where the energy is as a limited space, so we can evaluate what's changing. So the part of the universe that we're focused on, we're going to define as the system. So this is what we are focused on. We're going to call that the system. This is very important. Then we're going to call the surroundings everything around that. Everything around the system. I'm going to use these words more as we go forward, so they'll become more clear. There are 3 types of systems. We can have a open system, and that is when energy and matter can flow in and out of the system. So energy and matter can flow in and out. We can have a closed system, and that's when energy can flow in and out, but not matter. But not matter. And finally, I'm going to make this a little smaller. The final type we can have is an isolated system. And in an isolated system, neither energy or matter can get out or in. So these terms become more understandable with examples. So here's an example. I'll make my picture bigger. So this is a piston. There's gas in here. This is gas. It's contained in a container. And this piston, like a piston in your car, because that's what's in there, can go up and down. So if we push the piston down, we're adding energy to the system because we're confining these molecules. We're increasing their pressure. So by doing work on the system, we increase the energy of the gas by increasing their pressure. If we pull the piston out, we decrease the pressure. Or if the gas were to push the piston out, the gas would do work on the piston, and energy would leave. So energy can leave this system. Energy can be added to this system by whether the piston goes up or down. But no gas can get out. So what type of system is this? We have energy can leave, energy can be added, but matter cannot leave or be added. So we're going to call this a closed system. Energy can flow in and out depending on whether work or heat is being added or removed, but matter cannot enter or leave. So this is a closed system. So now I'm going to ask you a question. What do you think a human being is? Do you think a human being is a closed system, an open system, or an isolated system? Think about it. And the answer is a human being would be an open system because energy flows in and out of us. When we sweat, we're releasing energy. When we eat, we're taking in matter. I won't talk about how we get rid of matter, but we are matter and energy flow in and out of a human being. So we are open systems. Okay, so we've talked about that energy has to be conserved and that it can be transferred from kinetic energy to potential energy. So now we're going to define energy, those types of energies, a little bit more precisely from a macroscopic perspective. So there are two ways to transfer energy. One is to do work. We're going to define work as equal to a force times a distance, applying a force over a distance. So for example, if I were to pick up a baseball with my arm, there's my arm, there's my hand, and I'm going to throw this baseball, here's my body, I have a long arm. I'm going to throw the baseball over here so my daughter can hit it with her bat. I have transferred energy that is in my arm muscles, chemical energy actually, to the ball, so that ball can move over a distance. So I've applied a force to the ball, which comes from the energy in my arm. I've applied a force to the ball to make it move over a distance. So that combined force times distance is the work that I've done on that ball. I have done work to the ball. The ball did not fly by itself. So that's one way to transfer energy. I transferred energy that was stored in my arm and had to do work to make the ball move over a distance. A second way to transfer energy is heat. This usually accompanies work. And heat, so you want to write down this equation. Work equals force times distance. And now we're going to define heat. Heat is the transfer of energy from a warmer object to a colder object. Let's just make this smaller for right now. Small. Transfer of energy from a warmer object to a colder object. So let's take an example. We're going to have a combustion reaction. We're going to combust some methane. And the reaction is our system. The methane and the oxygen we're going to define. Remember we said we have to define our system. So here is where our reaction is happening, and we have our methane, our CH4, and our oxygen, and we're going to light that, and it's going to go kaboom. This is our system, just the reactants. When they react, they are going to release heat into the surroundings. This is the air surrounding the system is the surroundings. So they will have transferred energy from the potential energy in the molecules. They'll have transferred energy from their molecules to the surroundings in the form of heat. They have heated up the surroundings. So that is an example of heat being transferred from from a reaction. The system first was warmer, and then it transferred its heat to the surroundings. Another example, so we're going to leave it at that.